So this video is about the p-value, and the motivation for computing a p-value when doing a statistical test is the following. So what we did so far is we were testing hypotheses by means of acceptance and rejection regions, and we fixed the significance level alpha, and we didn't discuss any systematic way of choosing alpha, which is the probability of making a type 1 error. And so the question is, when it is very dangerous to reject a true hypothesis, so of a type 1 error, we should of course choose a very low alpha. But how low shall we choose alpha? Shall we choose 1% or 0.1% or even less? Yeah. So you can always, when you make alpha small enough, make sure that H0 is accepted. Yeah. So maybe if I illustrate this, so we have here F0, the distribution F0. So here we have the rejection region, yeah, this part and this part. And of course, if alpha becomes smaller, this line here moves to the left and this one to the right. So we can always move it so far that the value of the test statistics, so when I insert the concrete data, which I call here set ops, that this lies outside of the rejection region and inside of the exception region. Yeah, you just need to choose the alpha small enough. So also, let's say we choose a normal alpha and we don't move it around, and we get such a result. So we get a result where the test statistic falls really next to the border. So this is a completely different situation as if, let's say, Z is somewhere here. So it means, so we nearly accepted H0. So it was very close that we could do the rejection. And how can you report such a result? Yeah. So that's the idea of the p-value. You compute the p-value to have some quantitative measure of how sure you are about this rejection and about, let's say, the distance here between these lines here. So in a way, what you do is you try to test a hypothesis using all levels of significance. And then there are two cases. When you have very small values of your alpha, it is very unlikely to reject the hypothesis because you get very small rejection regions. Or you have a high significance level alpha, and then it will likely that you reject H0 and you have a large rejection region, and in a sense you can force that H0 is rejected. Yeah, you can do it the other way. You can move it here, yeah, by increasing the alpha. Yeah. Of course, this also works. So the p-value is the boundary value between the accept case and the reject case number 2. Yeah. So it's exactly the value is the lowest significance level alpha that forces rejection of H0. And at the same time, it's the highest significance level alpha that forces acceptance of H0. Yeah, so it is. So in this case, it would be here. Yeah, exactly where the set ops is. Well, not alpha itself, not the p-value itself, but you draw the line here, and then you have, this becomes your alpha, the area. Yeah, and then here the same. Yeah, you take here, yeah, that is minus Z ops, and you have this region here. Yeah. Okay, so usually alpha is something between 0.01 and, well, a small alpha, yeah, it could, let's say 0.5, yeah, something between 1 and 5. Oh, this is 50%. Oh, sorry. Between 1 and 10%, let's say, yeah. So this is the usual case. There are some exceptions, but usually you have something like this. So now when you compute a p-value that is inside this interval, you see that, well, if it's inside the interval, it's probably fine if you reject the hypothesis. And if the p-value exceeds 0.1, so if p is not in that interval, you could probably accept, yeah? Because for an alpha of 10%, you would already say, oh, I accept H0, and I cannot reject. So also when the p-value is smaller than 0.01%, it's clear that you can reject. Yeah? Even for such a small significance level like 1%, you reject it. Yeah? So you are very safe. This is what you see very often in papers, that people say, write something in brackets, like they say a statement and then they say p-value smaller, value smaller, and then very small number, 0.01 or even less, yeah? And then everybody knows, okay, this is a very safe situation, yeah? You can safely reject here because you have this very small p-value. So with a very low type 1 error, you can reject. So, but whenever p is in that interval, it is a bit unclear what you do, yeah? You have to think a bit about the level of significance then, and this is also called the too close to call, yeah? So this is a case where you are close to these boundaries. And a good decision is, in that case, to collect more data to get a more definite answer, yeah, for your test. So in that case, it's good to repeat the test with more data. Okay, once more to the formal definition of the p-value. So how to compute p? So you fix set ops equals set alpha, or alpha half for the two-sided case, or minus set alpha for the right-sided. So it depends here now. Fix this, that's right tail, left tail, and that is, that is two-sided. So next, after fixing this, okay, so I rearranged this a bit. So for the right tail case, we fix set alpha to be set ops, and this implies that p is the same as alpha is the same as the probability that set our test statistics, the distribution, so that this area of the distribution, so set is standard normally distributed, and that the probability of lying above set ops is exactly alpha is exactly p, and this is 1 minus phi of set ops in that case. For the left tail, we have here the minus set alpha, yeah, because we are comparing on the left side. So in that case, P is alpha is probability of Z being smaller equal Z ops or minus Z alpha is equal to so this is just phi of Z ops, and here in that case we have that P equals alpha is the probability that the absolute value of Z exceeds the value of the absolute value of Z ops, which is a Z alpha half. And well, this probability is a little bit more complicated. You can easily see that it's actually 2 times, put that here, 2 times 1 minus phi of Z ops, absolute value of Z ops. Yeah, because 1 minus Z ops is the it's alpha half, and then times 2 gives you alpha. Yeah. Okay, this is how to compute P for the standard normally distributed case for the Z test. So for a t-test, it's very similar. Just that instead of the standard normal distribution, you have the student's t-distribution. Okay. So let me finally add some words about the interpretation of the p-value. So here's this nice illustration from Wikipedia about the p-value. So recall, please, that the distribution here is the probability of Z, and that was always given H0 is true. Yeah, that is the distribution of Z given H0 is true. And well, from the definition of the p-value, it holds that that P, the value here, is the probability that observing a test statistic that is as least as extreme as the one that we have observed, yeah, that is here, yeah, that is exactly the p-value. So if so we cannot say anything about the probability that H0 is true. Yeah, P doesn't tell us anything about the probability that H0 is true. This is very important. Yeah, the p-value only tells us how this level here is, and if it is like here, yeah, we have observed something that is quite likely, yeah, and probably H0 is true, and if the p-value falls like here, yeah, then it is very unlikely that H0 is true, because we got this very strange, this very unlikely observation that fall here into this unlikely part of the distribution. So once again, to write it out, so P is the probability of observing a test statistic. Let's call it T in the general case. It's Z in the case of a standard normal distribution, but in the general case it's T. That is at least as extreme as the T-ops that we observed, right? This is here, yeah? And this area here is P, yeah? And this is all under the condition that H0 is true, yeah? So it's the probability that we observe something that is as extreme as the number T-ops that we computed, or even more extreme. Yeah? And if that probability is very small, we can safely reject H0. And if that number is high, yeah, like here, there is a lot of probability that you observe something that is as extreme or even more extreme as what we observed. So let me finish this video with an example. So we had earlier an example where we were considering a two-sided test to compare the quality of parts produced by two different manufacturers. And we computed a set value of the set ops of minus 0.945. So it's a two-sided test, and we would like to compute the p-value, and the p-value is, in case of the two-sided alternative, let me draw this. So this is the distribution of Z given H0 is true, and what we want is that these regions here have a probability p in the sum, so p half each of them, so the area is p half, and this value here for a standard normal distribution should be actually, so what we have is here minus 0.945, and here we have plus 0.945, and so the probability that some test statistic set, taking the absolute value, because we are only interested in, well, the how much it deviates, the absolute value deviates, that it deviates more than, well, absolute value of this. So this should be p, because, well, either it's negative, then we are here, or it's positive, then we are here. So that gives us probability that Z is greater or equal 0.945, that the absolute value is greater or equal this, which is 2 times, well, taking here 1 minus phi. Phi is the cumulative distribution function of the standard normal distribution, and plugging in the value, absolute value of Z ops. And because this here is actually, so this is p, should be p by 2, yeah, because that's exactly one of these two areas here. And yeah, we compute that this area has that is 0.34572, which is a lot. You remember that a good p-value is smaller than 0.1. So that means what we observed for Z is not very extreme. So assuming that H0 is true is a good assumption, and is not a contradiction to what we observe. So no contradiction with the assumption that H0 is true. And also recall that the probability of observing something that is as extreme or even more extreme than what the 0.945, so what we saw from the data, is 34%. Yeah, so it's quite likely. And so our assumption here about the distribution is a good assumption that H0 is true. Yeah, so this is relatively large. Let's draw it like this. Yeah. So here's a large area. And there is no contradiction to H0, and therefore we do not reject. But accept it. Okay.